Okay, what we're going to do today is we're going to talk about Bernoulli's principle. We talked about it with a lift, especially the classic, rather than the flow turning explanation for lift. And Bernoulli's principle is an area of physics and science. It's called fluid mechanics. Okay, so it's all about the flow of a fluid. Okay, air can be deemed to be a fluid as well. Now, pressure differences in fluids result in a change of velocity of the fluid. You could also reverse that statement and say a change of velocity of the fluid results in a pressure difference. Okay, so it's vice versa. Now, examples of this are things like a wing. We already talked about the wing at an angle of attack. As long as the flow is laminar over the wing, at the top surface, the flow of fluid is faster than on the bottom surface. Faster flow equals lower static pressure, okay? And that means we can also, they're likened in this equation here to energy. We'll talk about that in a moment. So you get lower static pressure on top, higher static pressure on the bottom, and the wing goes up. So wing's a good example. Car convertible roof. Now, if you're driving along really fast and you've got a soft top, the top, if you're going really fast, will lift, okay, because you've got that fast flowing air flowing over the top of it. A chimney. With a chimney, if you have a fire in a chimney, it's a narrowing area. So you have your fire down here, hot air rises, and as it approaches the chimney, it accelerates, okay? And when it accelerates, we get a lower static pressure and a higher dynamic pressure. Okay, so they're all good examples. So Daniel Bernoulli in the 1700s developed a principle and equation which relates pressure differences and velocity in fluids. Now, the conditions that he applied to this principle and this equation are that the flow has to be laminar, which is just a really fancy way of saying streamlined, not turbulent. And when we talked about angle of attack on a wing, as the angle of attack increases, we get more and more lift, and at some point in time, the flow is no longer laminar, and it becomes turbulent, and that's when we lose lift, okay, and Bernoulli's principle breaks down, okay? So we need to have laminar flow, and compressibility has to be very low, so you can't have a fluid that's really spongy and easy to compress, which is the way that hydraulic systems work, and oils and even water for that matter is very hard to compress. Air is a little bit compressible compared to, say, water and oil, but we can still apply Bernoulli's principle to it on some level. And then, of course, also viscosity. Now, viscosity is resistance to flow. So if something's highly viscous, a really good example of that when we're talking about material science is glass. Glass is a amorphous viscous solid. Okay, so it's a highly viscous. Essentially, it's a liquid, but it's flowing very, very slowly. Okay, so the equation, when we get to the equation, given that, and this is the explanation up here, so you might want to pause this and write this equation down. P is pressure, this is a rho, and its density, so how much mass for a given volume, and then we have a velocity of the fluid, okay? And Bernoulli's principle states pressure 1 plus this is actually the kinetic energy of pressure, or you could look at it as being dynamic pressure, is half rho v squared. Now, you might think that equation, if you're a physics student, looks a little bit familiar. Half mv squared, kinetic energy, okay? So that's why it's of that form, okay? So we've got pressure 1 plus that. Now, if we have a change in velocity, and we have V2 here indicating there's a change, so V1 and V2 will not be equal. When we have a change, P2 plus a half P, the second velocity is going to be the same. So basically, this side of the equation equals this side. So if pressure goes up, this has to go down, okay? If this goes down, this has to go up. So when this goes down, this has to speed up, okay? And you know, this might all sound very complex, but when you were a kid and you went to the park and you had a stream and you might be, you know, racing leaves on the stream together, you probably notice as you come to a narrow section that things speed up, okay? This is Bernoulli's principle in action, essentially. And as it comes out the other side, okay, because you've got a certain volume of fluid flowing, okay, and a certain pressure, when it gets to this point, all of this side has to balance with this side, okay? So to keep it balanced, we have a speeding up situation here, and then as it goes wide again, we slow down. You see it in rivers as well, whitewater rafting, or fast sections of the river tend to be the narrower sections, and then as the river opens up again, it slows down and it meanders along, okay? So that's an example of Bernoulli's principle, and like I said, the wing, you know, all that sort of thing. So in simple words, you can say pressure energy plus kinetic energy before any change is equal to pressure energy plus kinetic energy after the change. Or you can say the sum of the static pressure, which is the thing on a wing that causes a lift, plus the dynamic pressure is going to be equal to a constant. So if air speeds up, our static pressure has to go down. Okay, so, and once again, that's how we explain the classic lift. So I would pause this video now, and I would think to yourselves that you need to think about this first of all, and just remember that Bernoulli's principle is essentially about the relationship between pressure and volume, and that if we have an increase in speed of a fluid, we have a decrease in its pressure. Okay. Now this is being put to good use in an effect called the Venturi effect, which is essentially like this situation here. But we'll talk about that in the next video. Write down the information under fluid mechanics. Please write down what Bernoulli's principle is about, especially the things that need to be understood as having steady laminar state, laminar flow, compressibility and viscosity. Okay, those conditions that are essential for the equation to work reasonably well. And then this equation is probably worth remembering. At the very least, have an understanding of the principle. Okay, you need to understand it in a more qualitative rather than quantitative fashion for this course. Okay, that's me for Bernoulli's principle. Write it down and have a think about it.